Hi everyone, in this video I will provide detailed explanation of memory in LangGraph. So in LangGraph there are two types of memories. One is short-term memory and second one is long-term memory. So short-term memory is generally referred as checkpointer in LangGraph and long-term memory is referred as store in LangGraph. So short-term memory, the scope is per thread, which means at a conversation level, if we are building a conversational chatbot, the key that we use is always a thread ID and the lifetime is only for that conversation. Whatever conversation we are maintaining, the life of this short-term memory will remain in that conversation only. When a new conversation starts, this short-term memory will be reset. In terms of long-term memory, it is cross-thread. It is available everywhere, wherever we want to use. It, in terms of keys, it can have custom namespaces. It can be at a user level where we can use user ID as a unique identifier. It can be at an organization level. It can be at a location level. Whatever we want to set up, we can set up like that. Okay. And its lifetime is always permanent. Whenever we want to use it, we can use it. Unless we delete it, if it will remain. Also, one more thing in this long-term memory is that we have to maintain this manually. We have to store information manually here, which I will explain through all the examples. And I have prepared a comparison table also, which explains what happens when we are not using any memory versus only short-term memory versus only long-term memory versus both. Okay, so when we are not setting up any memory in LangGraph, then what happens? Every agent call starts fresh with no knowledge of past messages or users. So whenever we are calling the LangGraph graph, there is no information about the past, what happened. Okay, so it does not remember the previous messages. It does not remember user info, name, preferences, nothing, and it does not remember the information across threads also. Then when to use it? It is used for simple stateless tools or one-shot queries. So where we don't need any history, when we don't need any context, we don't need any memory. Okay. So next comes is the short-term memory. When we only use short-term memory, we refer to this as checkpointer. So here in this case, agent remembers the conversation history only inside one thread. One thread is one conversation, okay? But it forgets everything in a new conversation. When a new conversation starts, then short-term memory does not know anything. It remembers previous messages? Yes. Within the same thread, it will remember everything. Okay. Does it remember any user-specific information like name or any likes, dislikes, any preferences? No. Short-term memory will not remember that. Does it work across threads? No. So when the thread changes, then short-term memory is erased and reset. So when do we use it? We use it in case of chatbots and multi-step workflows. Okay, we are when we are not building very large applications where we want to capture the user behavior also, the important things about their behavior and use them. Then short-term memory is enough. Next is long-term memory. Long-term memory, what it does is that the agent remembers stored user details like names and preferences across conversations, but does not remember past messages. So when we are using long-term memory only, then the conversation history within that conversation is not available to the agent. Only the information that we explicitly save, like when the user tells his name, we save that. When the user says that, oh, I like these kind of things, I don't like these kind of things. So those preferences we save explicitly, that information only is remembered by the long-term memory. Does it remember previous messages? No. No conversation history is there. Does it remember user info, name preferences? The answer is yes. It is explicitly saved and it is always available to the agent. So does it work across threads? Yes. So it doesn't matter when how many new conversations we start, how many new threads we start. This information will always be available to agent for that particular user, for example, or for that particular location, for that particular company. So it will always be available. So when to use it? For personalization and user profiles. So when we want to remember and use certain things, let's say, for example, the user has provided a certain tone that always talk to me as a CEO of a company, for example. So this information the user has provided. Now that instruction will be saved in the long-term memory of the LangGraph flow. And then every time a new conversation or every time a message starts, this will be taken care. This will be considered that user wants the responses in this way only. Okay. So in those cases, long-term memory comes. So what is the most usual use case? This, which means that short-term memory and long-term memory both are used together in production grade AI assistants. Okay. So what happens here is that agent remembers conversation context and persistent user information like preferences and profile data. So it remembers the conversations also, the conversation history also, and it remembers the user information also. So whether like whatever are the users likes, dislikes, all of that it will remember. So here in this case, it will remember previous messages also because of short-term memory. It will remember user info also because of long-term memory, and it will work across threads also because of again long-term memory. So this is the most uh, the best way of using memory in LangGraph for production grade AI assistants. So we should use both. Now I will walk you through certain examples and tell you what happens in case of no memory, how it works with examples, what is happening. Okay. So let's come to no memory first. Simply we will import, then we will initialize our LLM. Here I'm using Groq because it is free. To understand how to use Groq API in LangGraph, LangChain for free, please click on the link in description. Now I'm defining the state. Here the state only need messages because I'm simply creating a conversational agent. That's all. So here what will be saved will be list of messages which can be of type based message. It can be an AI message, human message, assistant message, anything. And this is the reducer which is present in LangGraph automatically, which will keep appending the new messages here. Okay. So let's define the state. Now the assistant node, which is the only node we need. So we will take all the messages, we will send from the state, and then we will send those messages to LLM, and whatever response comes, we will send it to the messages field in form of a list because we are using add messages reducer here. Okay. So we define our node also. Let's quickly define our graph. So this is a very, very simple graph. Input comes to assistant node and then it returns the output. Okay, so now let's see what happens. So this graph is defined and we will send the message every time by calling the stream method. Stream method I'm calling because I want to see how many nodes are called. Here, although it is one node only, but in other examples, there are more than one nodes. So you will understand better what is happening in the graph. Okay. So when I say hi, it will say it's nice to meet you, is it something, etc. Okay. Message two is my name is Jatin. Okay. So here it has identified that okay, the person has told his name and it is just responding is in form of a greeting. So now in the next message, when I ask what is my name, then let's see what it says. So it will say, I don't know your name because we have not set up any memory here. So whenever we call the graph again, then it does not have any information about the past. Okay, what happened in the past? Like for example, this message, it does not. So this is without any memory. So now let's try to integrate short-term memory and see what happens in this particular example. And one more example we will see where long-term memory is needed. Okay. So we will import all the libraries, then we initialize our Groq LLM, then we define the short-term memory. So here in this case, I have put this in commented section because I will show you here that what happens if we only set up messages like this versus this with add messages reducer. Here it did not matter whether we keep it like this or like that, it does not matter. But here it will make a difference. I will tell you. First, we will use this one only, list of messages, and we use this add messages reducer. Okay. Next is, so let me try to clear all the outputs and then start it again. Yeah, imports, LLM, state, then assistant, which is using a memory. So here we will simply take the messages. This node is exactly the same as no memory one. So we just initialize it. Here we will build our graph. So this is the new part which is coming into picture for short-term memory. So for short-term memory, we define our check pointer. This is an in-memory saver we are using, which means that this memory will remain in the RAM of this notebook only. It will not be saved in any external database like maybe a Postgres database or something. For that also it is pretty simple, straightforward. The check pointer will be defined accordingly, and that information is properly available on the LangGraph documentation. So that is very simple. But for demonstration purpose, this is enough. Okay, so we simply use in-memory saver, and then this check pointer we pass when we compile our graph. Okay, we will simply say check pointer is equal to this. That's all. So now the short-term memory is set up for us. So when I try to run this, you will see how the graph looks like. It looks exactly the same, but the short-term memory is properly set up here. Okay. So how we will call this graph will also be a little different. So now let's say we start the conversation for thread 1 first. Okay. So this is the difference part. This part is different here. Earlier we were simply calling it like this, graph.stream. We were sending the messages and that's all. The node will be printed. But whenever we have a short-term memory setup, we will add this dictionary also, which will be configurable, and our thread ID will be the unique thread ID for which that conversation will be maintained. Okay, so whenever we change this thread ID, a new conversation or a new thread will be started. So I simply send this message. So this is the first message. Here it says, nice to meet you. Now I ask, tell my name is Jatin. Again, the same thread ID. This is very important. Okay, the thread ID, if it is same, only then the whole history of that particular thread will be maintained. So I simply say, my name is Jatin. It says, nice to meet you, Jatin. Now, if I ask, what is my name? So, and I use the same thread ID where I have sent all these previous messages. Now let's see what it says. It says, your name is Jatin. Okay, which was not happening in case of no memory. It does not know. Okay, but here also there is one very important catch. Okay, so if you are setting up your state like this, where you are using a reducer, then it will remember. But if I set up my state like this, then let's see what happens. I will try to set up a break here so that everything doesn't run. Okay, and I will restart and run everything. So here you see, I have told it here my thread ID is same. Thread ID T1, T1, T1. Okay, but it still does not know my name. The memory is all there, short-term memory, everything is there, which means that it does not really remember the whole conversation history. It always sends the previous state of the graph to the next next graph call. Okay, whenever this graph is called, it will send the previous state. So previous state, if we are setting up our messages to append every time the new message, then this initial state will be appended to the previous state. But if we are setting it up in a way that it overwrites every time, then all the previous messages are gone. They are no longer part of the history anymore. So this part is very important. If you are building a conversational agent with short-term memory, then the messages should always be set up like this. It cannot be like this, because then there is no conversation history that is maintained. So let me try to do it like this only and try to rerun again so that we can try out the other examples also. So now if we come here, so my name is Jatin is fine. What is my name? Your name is Jatin. So we are again back to the state where our conversational history is maintained. Okay. So now I will just remove this. And here, this is one example I want to show you where short-term memory will work fine, but long-term memory will not work. So if I ask, so here it is telling that what is my name? And if I ask what is my name, it will tell. If I tell him I am from Bangalore, that also it will remember within the same thread. You are from Bangalore, Jatin. It remembers my name also. It remembers where I'm from also. Now I change the thread ID to T2. Okay. So now if I ask call me by my name, it does not know because the thread has changed. So all the history that was there till this point, it was for T1. Now T2 is an absolutely new slate and it does not remember anything. Okay. So where I'm from, if I also ask, it does not know. I don't have any information. Okay. So within the thread, it will remember, and outside of thread, it will not remember. So if you want it to remember the user's name every time, irrespective of the threads, this is where the long-term memory will come into picture, and the location also can be one of the fields that we want to save. But everything has to be saved manually and explicitly. We will have to set up instructions in a way that these information are saved explicitly. It will not automatically save everything. Okay, so that will work across threads. So now let's come to only long-term memory and see how long-term memory remember things across threads and what are the limitations of long-term memory also. For that, first we will simply import, then our LLM, again the Groq LLM. Then this is an important part. Okay, so here what I'm trying to set up is that this agent will try to explicitly capture information from the user inputs. What it will capture: name of the user, the likes of the user in form of a list. So over a period of time, if the user tells multiple likes, then all of them will be captured, not only the uh, uh, last like, or like it will not be overwritten. Okay, now dislikes will also be saved, and preferences, all these things in form of a list, and name can only be one, so it will always be a string form. So for this is only for demonstration purpose that we are trying to save this information about the user into long-term memory permanently, but we can save any and everything whatever we want, but we will have to set that up properly. Okay, so this is a class that I'm maintaining because the agent that will do that will require to extract a structured output. For that purpose, this will be used, where we will define a LLM with structured output. Okay, so this is a state where I'm using the same way of messages, where it is list of base messages and add messages reducer is set up. And profile, I'm using the same class because I want to stream the agent, and I want to show that when the profile extraction agent runs, what it has captured. So this I can only tell if I'm saving that information in the state. Okay, so for that reason I've kept it. Otherwise, this will not be used in the conversation. Okay, because we will not take it from the state, we will simply take it from the store, the permanent, the long-term memory that we have set up. We will not use it from the state because the state will be reset every time a new thread starts. So it is better to like consistently use the store rather than the state. So now this extract profile node, this is a new node that we set up where we only give the last message to the agent, that like whatever input has come from the user, and we define this structured LLM where this is a class, we call it extractor, and we simply say extract user profile info if present, and extract the name only if it is a proper noun. So why I had to add this was because sometimes what was happening was that it was capturing user as a name of the user, because the input that goes is that type is equal to user, then message. So it was thinking that the name of the person is user. For that, I'm keeping it like this, that only proper noun should be captured and not user, assistant, or things like that. Okay, so that also I've done. And then I have put another condition here also to be double sure that these kind of names are not saved as names of the user. Okay. So this is the node where extract profile node will be done, and it will generate a structured output, and it will go to profile. Okay. So this node will only generate the information, but this is another node where it will save the information in the store. So how we will do it? We will try to uh, take the user ID from the config. The config we will send it when we call this node, and this will be the, so basically we are maintaining the permanent or long-term memory at the user level, but we can maintain it at any level here. Okay, so in our example it is at user level. So we will first extract if there is any existing information about profile for this user ID or not. If it is there, then it will save in existing. If existing exists, if it is not none, then profile will contain all these values. Okay. Otherwise, it will be like this. Everything will be none or blank. Here in this case, what will happen is that whatever information has already been captured, that will be stored in the profile dictionary. Okay. Now, the result will be from used as a state profile. Why we are using it? Because this node here has already extracted all the information from the latest input coming from the user, and it is saved in the profile field. So we use it from there. So chances are that in this particular message, it has only sent that my name is Jatin. So this one will have only information about the name of the user. So now we will check whether result contains what all of these informations. Okay, so chances are that only one or two of these will be available, remaining will be none. For that we are checking if name exists or if it is not none, and lower of this value is not in this. So sometimes LLM mistakes, or maybe because I'm using a free LLM, for that reason maybe it is capturing it like this also. But if we use a superior LLM, like for example GPT-4 or GPT-5, then chances are that it might not capture this information at all as a name. So if this exists in the result, then it will be overwritten in the profile dictionary that we have set up, okay, as a name. Same for likes. If it exists, then all the items that are saved, that are extracted in form of a list, they will all be appended to the likes list. Okay. Same for dislikes, same for preferences. Now, whatever the final profile dictionary we have set up, now we will save that profile dictionary into the store. Okay. The store also we will send into the node. Okay. The config also we will send, store also we will send. So store for that particular user ID, it will save in the profile dictionary as profile information. So we can set up as many information as possible, style of talking, or maybe uh, demographics, whatever information we want to, designation, whatever information we want to save, we can save. Okay, we can maintain the that particular type of nested JSON or a complex JSON in that store for this user. Okay, so now we will simply return profile as profile. This node will also return the profile because we want to override this. This was only having information about that particular message, but this is a final information. So it will contain information that was previously captured also. Chances are in the previous message it has captured already what is my name. So name was already there. But this message, this call only captured likes. So now the latest profile will have name as well as the likes. Okay. So we will simply run this node. So now we are using the assistant node, setting up the assistant node. In this one, our assistant node was only taking the message and returning the output, right? This one. But here what will happen is that whenever we send this message to the user, we will send this system message also along with the latest message, along with all the messages, where the system message will say this. The user profile is this. This is the name, likes, dislikes, preferences. Use this info if helpful. So basically, across threads, if the user asks, if the user has tell the bot that this is my name in one of the previous threads, and now if it in a new thread it is asking that what is my name, then this information will come handy, which is coming from the store. Okay. So here we have again extracted from the store for that user ID and the profile dictionary, basically the profile data, and that data we are simply using it here. Okay, so if it is not already there, then it will be a blank, and then everything is not already available. It can be the first ever message, but over a period of time this will be developed, which I will show you in the examples how it works. Now we'll simply just send all the messages, and whatever response comes we send to the messages field in form of a list. Okay, so this is the uh, like a proper way of setting up long-term memory, where whatever information we have explicitly captured, we always tell that also. Okay. Now we build that graph. Here, there are a lot of additional nodes. I will try to run this and show you. So from start, it will first go to extract profile, then it will update profile, okay? Then it will go to the assistant where the all information from the store is available, okay? So when in certain cases, when we have extracted a lot of information about the user or about the entity that we want to save information about, then in that case, we can use semantic search also to extract only the best matching information for our query and only send that, because chances are that we have uh, like thousands of entities we have extracted. So sending thousands of entities along with every message will try to consume a lot of tokens, or in some cases, it might not even fit in the tokens. It will exceed the token limit. So in those cases, semantic searches set up, and then top n entities only are extracted and sent to the LLM. If you want to see how to set that up, please let me know in comments, and I will try to set up another example around that. Okay. So now this is the bot which uses long-term memory. Now we will see some examples how it works. So here we are using the configurable as user ID. In short-term memory, we always use the thread ID. Okay. So this is the difference. We are using user ID here. Okay. And okay. So sorry. One more difference is that in short-term memory, we were using in-memory saver as a checkpointer. Here we are using in-memory store as a store. Okay. So here it was a checkpointer and here it is a store. So this also will be replaced by a permanent database, which should be very easy to set up. But for demonstration purpose, this is enough, which is inside the memory of this notebook. Okay, so that is important. Now I have sent this message and let us see. Here we were streaming and there were multiple nodes involved. First will be the extract profile. It did not extract anything because the user did not tell anything about likes, dislikes, preferences on name. Okay. So next is the update. Update also did not do anything. Okay. It did not extract anything. And the latest profile does not contain anything. But the assistant will say it will just respond to the greeting. Now let's see what is there in the store. So how to access the store? Store.get users u1. Then we want the profile in form of a dictionary. So here, if you see, nothing is there. Name is none, likes is blank, blank list, blank list. Okay. So nothing is there. But as and when as we ask more questions, this will keep getting updated, as you see. So now I will say my name is Jatin, and again the same configurable I'm using, same user ID. Now let's see what happens. Here, extract profile has extracted name, but nothing else was available. So update profile has updated the name here, but this information is still missing. And this is a usual response from the bot. Okay. Now let's see what is there in the store. In the store, now the name exists, but other information is still not there. Now I will only provide about my likes and the name will still be retained. So I am telling I like Tesla stocks to the same user ID. Now let's see what happens. So the extract does not have any other information. It will only extract based on the message that has gone to the node. Okay, it does not remember what is there already there in the store. But update profile knows. Update profile knows that the store already exists, contains name. Now likes also has to be added, which is Tesla stocks, and dislike and preferences are still not there. So this is a usual message, which is okay. Now let's see what is there in the store. Now in the store, name is also there and stocks are also there. Now I add a dislike. Again, here it captured only dislike and nothing else. Now the latest store contains name also, likes also, dislikes also. Okay. And this is the message which doesn't matter. Now it contains these three information. So incrementally, it will keep adding in the store explicitly that we have set up our agent in a way that first thing it will do is that it will try to capture information that is important and save it in the long-term memory. Okay. So now if we ask, who am I? to the same user ID. Now there is no concept of thread here. Okay, so we can only rely on the long-term memory. So now it says you are Jatin because it was able to use the information present in the store, which is this information. Okay, but there is a limitation to this one also, that we are only saving this information: name, likes, dislikes, preferences. But for example, there is a location also. User tells I am from Bangalore, for example. Okay, but this information we are not saving at all. So if you see, extract profile does not know anything. It did not extract the location. It did not save it also. And this is a message which doesn't matter. But now if I ask I am from which city, using the long-term memory, it does not know. I don't have that information because that information was not explicitly saved in the long-term memory. So this is where the combination of short-term memory and long-term memory comes into picture, that sometimes within the thread also we want some information to be saved and reuse it, but outside a thread also we want certain information where long-term memory will come into picture. So whenever we want to build production grade solutions, we will set up both long-term memory and short-term memory, which is in this example. I will quickly run you through all the imports: LLM, then profile update class, then the state all contains the messages in form of this with this reducer and the profile. Everything is the same. The only when we compile it will be a little different. Okay, so this one extract profile node is also the same. It will use the structured LLM. Now profile builder is also exactly the same. Assistant is also the same. It is using information from uh, the long-term memory also, and it is sending all the messages which are coming from the. So here in this case, since short-term memory will also be set up, so all conversation history will be maintained for that particular thread. So I run this and I will show you how it works. So this is also exactly the same. The only difference is that we have set up store also, which is in memory store, and we have set up a checkpointer also, which is using in memory saver. And when we compile it, we send both these informations. This is for short-term memory. This is for long-term memory. We send both. Okay, so both will be set up and both will be used properly. Otherwise, the graph looks exactly same as long-term memory. So now we will define the threads also. In long-term memory, there was no concept of thread, only user ID was there. Now we have a thread also, T1, and a user ID also, U1. Simply ask hi. So these are the steps that ran because we are streaming it. Now let's see whether anything was captured. Nothing. Here also you could see nothing was captured. Now I tell my name is Jatin. So now it has captured name and it has saved it in the this field in the profile for U1 only. Okay. So this is a message, doesn't matter. Let's see what is saved in the store name. Next is again likes and dislikes. It has saved likes, updated in the store, dislikes, updated in the store. Now let's say, now if I say I am from Bangalore, and now if I ask which city I'm from, then it will tell. For same thread, it doesn't matter whether that information is saved in the long-term memory or not. It will still answer. You are from Bangalore. So this is where it comes into picture. Okay. So now if I change the thread, this information will still be available, which we could already see in the long-term memory example, but I will show you how it works. If I say, who am I? Then it will simply say, you are Jatin. So now the thread has changed. It is T2. Okay. This did not work in case of short-term memory, and this did not work in case of long-term memory only. But when we use a combination, both of them are working. And if we see the store, this is the information that is already saved, which will be reused. Okay. So this is all about memory in LangGraph, short-term memory and long-term memory. Short-term memory for that conversation only, and long-term memory which will be permanent but explicitly saved for that particular user, location, company, anything. So it is up to us how we set it up. Okay, so but the best way is to use both of them in combinations. So that's all for this video. Please let me know in comment section what other details you would like to see around memory or LangGraph and AI in general. Please subscribe to my channel. Thank you for watching. Bye.